All right, good afternoon, everyone. Welcome to Intro to Space Nav Spring 2025, Lecture 26. So I was mistaken before. I had said that Lecture 25 was going to be the second to last lecture. I was wrong. Turns out it takes longer than one lecture slot to get through image features and visual odometry. So just to reiterate what I said a second ago before we started the recording, Lecture 26 is going to be visual odometry part 2 and crater navigation part 1. And then lecture 27, which was originally going to be a guest lecture, is going to be crater navigation part 2. And then I am done downlinking information to you. And then the very last lecture will be a guest lecture from a colleague of mine. And I'd like to try to get to the point where, like at this point, y'all have all the information that you need to do homework 5 and homework 6. That's all already posted. So this lecture is for people that are trying to do homework 8 or homework 7. So homework 7 is the crater-based navigation lecture, which we'll get to in the second half of today's discussion. And then homework 8 is visual odometry, which we're about to wrap up. So as a reminder, let's kind of quickly skim through our notes from lecture 25. So my question in lecture 25 was, if you've got two kind of rapid before and after images of the surface of the moon, and you know that the spacecraft that took those images moved, then what you ought to be able to do is track the motion of points of interest in the image and go, well, really, those points didn't move, I moved. Right? That's kind of the basic idea behind visual odometry. Now, this relies on the ability to reliably detect and identify features in an image. And this is actually a pretty richly studied area that involves image features. And so some of the common image features are SIFT, SURF, orb, K's, brisk, Harris corners. There's several other ones. SIFT is kind of the most popular one. I think that most people know about SIFT. But it is not necessarily the fastest or the most robust. It's just kind of the one with the most popular name attached to it. But the other ones are also really good. We are talking about SIFT in this class, and I gave a quick rundown, well, more than a quick rundown, of what's going on under the hood with SIFT, and it has to do with being able to reliably find points in image A and find those same points in image B, and in both cases say, something about this point is interesting, I'm going to save this. And then the question is, how do you save it? How do you save it in such a way that you can look it up later? And that is with a feature descriptor. So there's feature detection and then feature description. And in SIFT, description takes the form of a 128 element feature vector, which if you're trying to compare the features in image A to the features in image B, then you need to have relatively close feature descriptor vectors. And then there's going to be a little bit of wiggle room because you're never going to get exactly the same feature descriptor. Even between two images with a very mild amount of change between them. It's going to be a little bit different. And what's going to end up happening is you will have detected features, and then of those detected features, only some of them will match, right? You've got the detected features in A, detected features in B. The points that have a correspondence between them is only a subset of those. And then, even within the matched features, there will be some that are wrong, right? There will be cases where a feature in image A maps to a point in image B that you can see with your eyes is not correct. And that sort of thing will happen. You'll get these false positive matches with SIFT features. And so what we implement is something called random sample consensus, or RANSAC, which allows us to go, no, we're only going to take the matched features that seem to tell the same story, if that makes sense. And that story is, what is the rotation and translation of the camera between the two images? And this many inliers all agree with the same story, and that's the largest number of inliers we can find with the data. We're going to go with that. That's basically the idea. And the net effect of all of this, of our SIFT features, is we get something like this, where we have image features in image 1, image features in image 2. We see the correspondence between them. We see that they have moved. And so now we've got kind of before points and corresponding after points, which might sound a little tiny bit like Waba's problem, right? We know with Waba's problem, if you have line of sight vectors in frame number 1 and line of sight vectors in frame number 2, and you know that it's the same vectors just expressed two different ways, then you can solve Waba's problem through any of a number of techniques to find the attitude transformation matrix or the quaternion that maps from kind of frame A to frame B, or frame 1 to frame 2, right? This is a little bit different because the physics governing the situation is not that the camera rotated only. We assume that the camera did rotate, but the camera also did translate, and that's kind of what this diagram is trying to get at. Imagine you have a camera orbiting the moon, it takes an image, and after a rotation and a translation and some time elapses, pardon me, it takes another image and it finds the same point, right? This would be the same SIF feature in both images. What you end up with then is E, which is a line of sight direction. So EIM in the moon frame, we're ultimately going to be measuring in the camera frame. But the idea here is line of sight direction in the camera frame to a point, and line of sight direction in the next camera frame to the same point. And there's some sort of rotation and translation happening between time k-1 and time k. And after quite a bit of fancy derivation, we ended up on this equation, which is going to be where we start today's discussion. But any questions on our review from last lecture? So this is going to be visual odometry part 2. And previously on Lost in Space, sorry, that's a dumb reference, we had this equation here. Yep. I'll just erase this stray mark. I want to make sure I didn't just delete the original. Nope, okay, looks good. So this is our equation from last time, where you could think of the bit on the left here as the after unit vector. And I'll say vectors, plural. And then this bit over here is the before unit vector, or unit vectors. That's the math problem that we're left with. Okay, so all of our interesting state information, which is our rotation and our translation, lives in the E matrix. And our measurements are on the sides. So you can imagine what we're left with is, how exactly do we set up this math problem to solve for E? And then even if we knew E, can we back out our rotation and translation? That's kind of where we're going. This equation has a name. It's called the epipolar constraint. And E also has a name. It is the essential matrix. From stereo image processing. Those of you that have experience with stereo image processing, a lot of familiarity, a lot of kind of, oh, hey, I've seen this before, should be ringing in your head. At least I hope so. I hope I explained this well enough. Because it's the same math. So here's the kind of mind-blown moment. And this occurred to me just a few months ago because I was doing some work on visual odometry, and I was doing some different work on stereo image processing. And when I realized it's the same math, I had this kind of, brain explosion moment. I was like, oh my goodness, this is incredible. But if you think about it, it makes perfect sense. You've got a camera taking an image of a point, and it doesn't really make a difference if you have a different camera taking an image of the same point at the same time, or if you have the same camera taking an image of the same point at a later time. Either way, it's two cameras, right? Either before and after, or camera A, camera B, taking an image of the same point, and you're trying to estimate the rotation and translation between the two cameras. That is extrinsic stereo camera calibration, right? This is actually a well-studied math problem. So we can use some of the math from extrinsic stereo camera calibration to find the rotation and translation between not our two cameras, but our one camera at two different times. So hopefully this rings familiar if you have done this type of thing before. So I'll say monocular visual odometry has the same mathematical structure as stereo camera calibration, and the same limitations. So in both cases, we want rotation and translation between two cameras. And in both cases, we have a range ambiguity problem. Right. We can only find, and I kind of alluded to this last time too, we can only find the direction of motion, or I'll say the direction of delta R, not its magnitude. In the same vein, if you're trying to do extrinsic camera calibration, you can find the direction from camera A to camera B in the camera A frame or in the camera B frame, right? Either way, you can find the direction between the two of them, but you won't find the distance between the two of them by using this method, right? There are other methods you can use to find the distance. Generally, with stereo cameras, you can just measure the distance directly and then put that into one of your config tables. And that's ultimately what gives scale to the entire problem. Or with monocular visual odometry, you can combine this information with information from like a laser altimeter or a radar altimeter or something like that. You need some other measurement source to kind of give scale to the problem. You know, am I going very high and very, very fast, or am I lower and slower? And you know, we still end up with like a similar triangle problem, right? That sort of thing. So in either case, next is to solve for E and extract state info. So there is a method of solving for E giving this type of problem, and it has a name. It is called the 8-point algorithm. Okay, we're going to start by abbreviating the above equation to, now it's going to look like this. E2 hat transpose, capital E, E1 hat equals 0. Right, it's the exact same as before. I just thought let's kind of simplify the notation here. So we basically have the E before and the E after, and we seek the capital E. Now, how do we solve this? We know how to solve problems that look like AX equals B. We can do that, right? That's a linear system of equations. You can solve that with least squares. And we may even know how to solve problems that look like AX is equal to a vector of zeros, which is what's called a null space problem. Maybe you've heard of this. If you are not familiar with AX equals 0 type problems, we will go over it later in this class. But this is what's called a null space problem. So what we want to do is we will manipulate our equation into a null space problem. Okay. So this is where ordinarily I shy away from component-wise analysis of a matrix vector equation, right? Matrix vector equations are so neat and tidy, and when you break it back up into its scalar terms, it gets pretty nasty pretty quickly. However, in this case, we're going to see something really cool happens. And the metaphor that I have for it is, you know, when a caterpillar turns into a butterfly, it has to kind of, you know, make a little cocoon, and then it lives in the cocoon, and then it, you know, metamorphosizes into a butterfly. While it does that, like in the cocoon, the caterpillar turns into a liquid. Basically, it just completely breaks down and then reforms into a new being. And similarly, our equation is going to break down into something incredibly ugly, and then it's going to reform into a new equation, which is maybe even prettier than the original one. And I say that, and I could be wrong. I read that caterpillars turn into a liquid on the internet, and I am not a biologist, so I could be wrong about that. But it's a cool metaphor for what's about to happen next. So our equation is going to look like this: E2x, E2y, E2z, E11, E12, E13. You can see where I'm going with this. 2, 3, 3, 1, 3, 2, 3, 3. Okay. And then this multiplies E1x, E1y, E1z. Okay. If we multiply this all out, which we are going to, then what this is really saying is, okay, here we go. E2x, E11, E1x plus. This is going to be really annoying. There's about to be 3, 4, 5, 6, 7, 9 terms. Then we've got E2x, E12, E1y, E2x, E13, E1z, E2y, E21, E1x, E2y, E22, E1y, E2y, E23, E1z, E2z, E31, X, E2z, E32, E1y, E2z, E33, E1z is equal to 0. Okay, ugly, I get it. Here comes the butterfly. We can just as easily rearrange this equation to look like this. Get E2x, E1x, E2x, E1y, E2x, E1z, E2y, E1x, E2y, E1y, E2y, E1z, E2z, E1x, E2z, E1y. This is where I'm going to cheat because I have one note and you don't. Sorry. I ran out of space. And then E2Z, E1C. Go. And then this is going to be a row vector that multiplies a column vector that looks like E11, E12, E13, E21, E22, E23, E31, E32, E33, where this vector I'm going to call E vector. This is the vectorized form of the matrix E. So all we really did was took our original equation and then reshaped it into a giant row vector formed by this kind of linear combination of our terms and our before and after line of sight vectors, multiplying this column vector, which is the vector form of the matrix E. So imagine then that we're not really done because this is one equation. And if we're trying to solve for E, capital E, we are going to need how many data points? Right? How do we set up this equation so that we have enough data points to solve this problem? Anyone want to take a guess? What if I scroll up to the header on this section?
Are you going to need to take, well, eight images before you'd be able to do this?
Not 8 images, but 8 points in 2 images, right? Because you've got, in this case, E1 is from image 1, and then E2 is from image 2. And so we actually have enough information, right? Did I draw it with 8 points? 2, 3, 4, 5, 6. No, I did not. But imagine that there were 8 points that you were tracking or more, right? There's going to be quite a few more. If you do homework 8 and you get SIF features from image 1 and SIF features from image 2, there will be hundreds of corresponding features, not 8. And I would say, might as well just use all of them. But yep, so we can do this with 2 images and at least 8 points. Might as well use every point. That's my philosophy, at least. But we now have a null space problem of the form AX equals 0. We need at least 8 points to solve this. So that's where we get the name 8-point algorithm. Very cleverly named. I recommend using every point you have. Or every matching point pair you have after ransack. Okay, so now at this point, I'm assuming that you've done your image processing, you've found your corresponding points, you've set up your equation. We haven't actually talked about solving a null space problem yet. So let's take a minute and talk about that. So solving a null space problem. This is going to be a short section. There's a fundamental difference between a null space problem and a least squares problem setup of the type AX equals B, because AX equals 0 gives us this ambiguity problem, right? So remember that if AX equals 0, then so does 2AX, right? So your solution could be X, but it could just as easily be 2X, or it could be 3X. You're going to end up finding X to an unknown scale, and that's just what you got. Right? You can force X to be a unit vector. You can apply any other constraints you want, but ultimately you are imposing that constraint, not physics, right? Because we have a null space problem, we've lost our overall scale to the problem, which that ultimately means that when we're solving for our rotation and our translation, we can find the rotation just fine. It's the translation that we're going to lose distance information. So given a problem of the form ax equals a vector of zeros, perform singular value decomposition A is equal to U sigma V transpose. And the solution for X is the column of V transpose that corresponds to the smallest singular value. So generally, that's the last column of V transpose, depending on the way that MATLAB or Python spits out your singular value decomposition. Right? So what we're really saying is there is some matrix A which has a null space. That null space is, here's a perfectly good vector X, which is not of length 0. It's a real vector. And this real vector X, if you multiply it by A, it goes to 0. And the other thing about that is that vector X, if you were to double its length and multiply it by A, it would still go to 0. And what really is, X is a direction in 3D space that is more or less kind of ignored by A, if that makes sense. That if you multiply any vector along that direction by A in space, you get 0. That's the meaning of a null space problem. So there's something about A where essentially it's going to have at least one basically 0 singular value. And the corresponding column, corresponding vector that you extract from V transpose is the direction saying there is no A in this direction, if that makes sense. That's kind of how I think about it. So let's see. The downside, this is we can only ever know the direction of X. So we can give up on ever finding. Remember, what we were originally after is delta R in the camera K frame. The best we can do is delta R in the camera K frame unit vector. So this is a unit vector, and it is the direction of motion. And that's about it. In the limit, as tk minus 1, which is just delta t, goes to 0, then this, not delta c, this delta r hat ck becomes the velocity direction. Or what's known as the heading. So you remember learning that velocity is speed with a direction. Speed is the scalar of velocity. It's the norm of your velocity vector. If you normalize your velocity vector, which is you lose the actual speed part, you just know the direction that you're going. That's like heading. That's the idea. So imagine that you're a ship's captain and you're talking to the navigator and say, oh, what is our heading? our compass heading. What direction are we heading in? That's the idea. We're finding the direction of motion or the direction of velocity, not its distance. Interestingly enough, if you have enough heading information over time for an orbiting body, you can use that to perform orbit determination and ultimately get the full state of the vehicle, which is pretty slick. So visual odometry is a complete breakfast if you get enough measurements over enough time to let things converge. But anyway, for now, what we are after is this delta R hat, which is a unit vector. Okay, good point to pause for questions. Everybody good? You might say, Paul, we found E, but we still haven't found delta R. It's like, yeah, I get it. We're doing that next. But as long as nobody's stuck. Okay. The last bit is extracting state information. Right. Again, we will abbreviate delta R hat CK. I'm just going to call it R. And T CK minus 1 to CK, the direction cosine matrix from the camera at time K minus 1 to time K. So this is basically the rotation. We're just going to call that T. Okay. And we will recall that the essential matrix is really R cross, which is a 3 by 3, multiplied by T, which is another 3 by 3. So how do we find R and T given the fact that we know E? So we will again start by performing singular value decomposition. E is equal to U sigma V transpose. And I'll just say, do not mix up with our SVD of A. So when I coded this up, I said like U underscore E, and then up here it's U underscore A. Find some way to make sure that you don't get these matrices mixed up. Okay. We will define two matrices. So here's a matrix called W, which is 0, -1, 0, 1, 0, 0, 0, 0, 1. And matrix called Z, which is 0, 1, 0, -1, 0, 0, and then 0, 0, 0. And the answer, and I don't want to bog us down by spending a lot of time proving this. So for now, I'm just going to drop this answer in your lap. The answer, without proof, is T. There's going to be some ambiguity here. There's going to be multiple possible solutions. T is either going to be UW V transpose, or T is going to be UW transpose V transpose. And then similarly, R cross is going to be plus or minus UZ V transpose. Okay. And then it's trivial to get R from R cross, right? We're just undoing the cross product matrix. Okay. And then I'll say, remember to enforce unity norm constraint on R when you're done. Okay. Still, we will have ambiguity in our solution. This leaves ambiguity in our solution. So we've got two possible T, and we've got 2 possible R, for a total of 4 candidate answers. Okay, first of all, I'll make a note here. If you're finding that your determinant of your T that you're getting is -1, try negating E. I ran into that when I was coding this up. There's nothing in here that is explicitly forcing T to be a right-handed direction cosine matrix. It could be a left-handed direction cosine matrix. The equations would all still be valid. The math would still math. So you'll need to go in there and say, oh, wait a minute. If when I solve for T, my determinant is -1, we have a left-handed rotation, let's go back and solve this problem again, but with -E. Okay. Even so, the way that we would handle our ambiguity is, note, try to project or triangulate points using your candidate answer, candidate R and T. Only one combination will consistently put points in front of your camera. So choose that one. And that's it. So that allows us to find T and R, and we can put them through a sanity check. You can also put them through a sanity check just by looking at your image, right? If we go all the way back to our diagram at the beginning of the last lecture, clearly what's happening here is you're translating along the x-axis. And actually, so imagine that this is your x-axis here, and then this is your y-axis, and then z is into the page, then it sure looks like, as we went from image 1 to image 2, that we moved mostly along the positive x-axis because everything moved to the left. So if you're, and it also looks like there's almost no rotation. Right? Now, another possibility is you stood still and you cranked the camera to the right. That actually might also do something similar to this. So there is some ambiguity there in your solution. But basically, as it appears, it sure looks like the camera stood still, so there should be almost no rotation. The translation should be all in the positive x direction. So you can look at the images that I posted for homework 8, and you ought to be able to see with your eyes, like, oh, I think I'm moving mostly in this direction. And you can use that as a kind of a gut check to kind of test your candidate answers. That's about it. So that is everything you need for homework 8. Any questions on visual odometry? Cool stuff. Okay. I know we're a little bit early for our break, but this is a great natural stopping point because I'd like to come back and talk about craters. So why don't we take about 5 minutes to cool it, and then we will talk about crater-based navigation. It's about 6:40. We'll round it to 6:43 for y'all. So let's take a break till 6:48. Okay, welcome back, everybody. So I want to talk about something that might look a little bit similar, but it is fundamentally different than what we've talked about for visual odometry, and that is crater-based navigation. So this is crater-based navigation. The basic premise might look a little bit similar here. So imagine that you have an image, looks like this. And, nope, pull it, there we go. Imagine maybe your image looks like this one, where this is the blackness of space. And then here you've got crater, another crater, maybe a huge crater, smaller one, two of them over here, another one down there. Where, just to be clear, these are craters. You can navigate using only this image. So before, we had talked about how you could navigate using a pair of images. You could basically use a before and after set of images to determine how much you had moved. And what was neat was if you did sift images on image A and sift images on image B, you never need to actually know where these points are on the surface of the moon. You just know, hey, that is a static point that moved, and now I can find my rotation and translation. We're looking at it kind of a different way here, where instead you can find an actual unique solution to where am I over the surface of the moon. The thing is, you're going to need to identify your crater. So you basically have an easier problem and a harder problem. Actually, I take it back. I think a better way to think of it is this is a harder problem with a greater reward at the end of it. So visual odometry is relatively simple. Crater-based navigation is harder. However, you can actually get an answer for where am I, like in a global sense. Right? And the way we would do this is we would say, okay, let's actually go through and identify this crater here and this crater here and this crater here. Find out where they actually are, and I can take the centers of these three craters and I can find my position in space, which is not quite triangulation. It's something a little bit different, which we're going to talk about probably next time. I don't think we'll get all the way through it today. But we do actually have to identify craters, but when we're done, we get an actual solution for position, not just, my before and after change in position. So first of all, I'll mention that, here we go, navigating relative to features on the surface of a planet, moon, or asteroid is called terrain relative navigation, or TRN. And this is an area of active research. People are working on this today, right? This is not 10 years old or even 20 years old. This is like ongoing. We don't have this problem all the way solved yet. So terrain features can be identified for global pose, which is what I was talking about a second ago. Basically, you could say, I know my latitude and longitude and altitude because I know that crater's name. And, where I see it in my image. Let's see. What you'll notice is crater-based navigation shares many similarities with star trackers. Okay, so there's going to be 4 steps. If you remember all the way back in our star tracker lecture, lecture 16, or first star tracker lecture, I said there's going to be 4 steps on how to make a star tracker work, right? We know that we have to be able to process a star field image to find directions to stars. We need to process a catalog of where are all the stars into information that is basically something we could compute if we had it in the image. Then we have to solve the star identification problem, which everybody's all done with homework 4. You know what a doozy that is. And then the easiest part is at the end where you actually finish the math problem and you say, okay, in my left hand, I have all of these directions in 3D space in the camera frame. In my right hand, I have the same directions in the global or the inertial frame. I can find the attitude transformation matrix that maps from the inertial to the camera frame, right? Here, it's going to be pretty similar. So let me start breaking this up into 4 quadrants that are roughly equal in size. Okay. First step is image processing, where we'll say, okay, here's a crater image, there's a crater, there's a crater, there's a crater, maybe there's a big crater here, smaller crater out there. And we're going to detect craters in the image and basically build a triangle of craters the same way that we detected stars and built a triangle of stars. Similar concept here. Oh, sorry, I'm trying to erase. So this would be crater detection in an image. Okay. The next is we would need a map of on the surface of the moon, where are all the craters? Which I realize I'm basically drawing a chocolate chip cookie here. But this would be lunar crater database generation. Okay. The third is going to look shockingly similar. Invariant 1, invariant 2, invariant 3. There's a whole bunch of points in invariant space. We are looking for an index query within invariant space. It's going to look like this. And this is going to look mighty similar. Pretty much use the same diagram. This is not invariant based star ID, but it is invariant based crater ID. You might be saying, Paul, surely there aren't invariants for craters. Surely there's nothing about a triad of craters that is the same no matter how you look at it. And I would say, au contraire, they are not the same as intercrater angles because intercrater angles are not invariant, but there are mathematical constructs that we can compute for a set of craters in our image, which will be the same no matter how you project them into your image. And then finally, we actually solve the math problem that we came here to solve, which is if I know that this is the moon, and I know that I found this crater and this crater and this crater, and there ought to be only one position that makes sense. Oops, try that again. There ought to be only one position that makes sense for my spacecraft. And this is relative pose estimation. So you see, hopefully, the correspondence where there's image processing, there is database generation, there is invariant-based index searching, and there is actually solving the math problem to find your pose, right? Now, you might look at this and say, dear God, homework 4 was awful. A homework 7 surely is going to kill me if it's even harder. And I will say, crater-based navigation is considerably harder than a star tracker. There's a lot more going on. Each of these steps is a lot more complicated, pound for pound, than the corresponding step in star-based navigation. So you might say, oh my goodness, there's no way I'm going to be able to do homework 7. But relax, homework 7 is easier than homework 4. I've basically cut out several of these steps for y'all because I want it to be something that you could actually solve. What we will focus on in this class is this fourth step, relative pose estimation. We're going to talk about the other three, but those aren't going to show up on your homework. There's going to be no database searching on homework 7. There's going to be not even any image processing in homework 7. You're literally just going to code up and solve the relative pose estimation step, which is harder than Waba's problem, but it's still way easier than homework 4. So we will focus on the fourth step, but we will at least discuss the other three. So I'll also mention, if you would like to read more, one of the best recent papers on this topic is Lunar Crater Identification in Digital Images by Christian Dirksen and Watkins, published in 2021. And I would say Ann McKee, because I'm in the acknowledgments of this paper. I'm not a co-author. I can't claim that, but I was instrumental in cranking out some of the data to help prove some of these concepts. So I was proud to be a part of this. And this is also kind of an area of active research. Like people are still looking into this at NASA. There's some of the most recent missions to the moon have demonstrated crater-based navigation on board. And so like this is hot off the presses stuff. This is still going on today. So what's going to happen next for the next 2 pages worth of yapping, and then we'll wrap up, is I want to talk about crater detection, crater databases, crater ID. I'm going to set up the pose estimation problem, and then we will finish it next time, and then that'll be it. So it's going to be a very short lecture for lecture 27, which will give us ample time for office hours. So questions before we move into crater detection? Cool, okay. Crater detection. So I'll start by saying that detecting craters in an image is more of an art than a science. There are many many published methods using classical image processing techniques and machine learning. And this is an area of active research. People are still looking into this. So classical methods often leverage some a priori state information. So this would be something like, at least we know our sun direction or our illumination direction. Okay. So let me draw a quick little sketch of how this might go. Yeah. So what you'll notice is if you look at a photo of the surface of the moon, and don't trust myself to draw a circle very well here. There's your crater. What you'll notice is that there is a particularly bright region on one side of the crater and a particularly dark region on the other side of the crater, right? This would be the shadow of the crater rim here. And then this would be the lit portion on the opposite side, which is extra bright because it's kind of catching extra sun. Right? And this direction is the illumination direction. So here's kind of incoming sunlight. And you'll see that this dark crescent and this bright crescent are along that sun line of sight direction from each other. They correspond to one another. So a classical image processing technique would look like basically each crater has a shadow region and what I say equal and opposite bright region. So dark and bright regions can be correlated along the sun direction. So you might say, well, look, you've got roughly as many dark pixels as there are bright pixels for this particular crater. And you've got a blob of dark pixels and a blob of light pixels where the centers of them lie along one of these parallel rays governed by the sun illumination direction. So that's kind of how we detect, like, oh, I suspect that this dark region and this bright region represent the outside of a crater rim. And so then you fit an ellipse to each candidate crater. Now, this type of thing means that you need to know the sun illumination direction beforehand. And if there are mistakes in your sun illumination direction, that's going to cascade to problems with your image processing. Also, there can be plenty of false positives and false negatives, right? So there are definitely still issues with this method. Another method is machine learning techniques. So machine learning techniques typically involve a neural network. And if I do say so myself, if I'm allowed to give my opinion, this feels like a neural network problem. This feels like the sort of thing that neural networks were built to do. So typically involve neural network. Okay. And so I'll draw a little sketch here too. So you would train a neural net on many, I'll say myriad, sample images. With craters found by hand. And coming up with these training images is difficult. Okay. So you might say, why don't we just take a compendium of all the photos that anyone's ever taken of the moon and start training a neural net based on those? And it's like, well, a lot of those images are going to have different intrinsic and distortion parameters, but let's say we just stuck with the Apollo images, all the images that the astronauts took of the moon during the Apollo missions. You also need truth data. You need to be able to say, oh, when I took this image, I was at this altitude over this latitude and longitude. And we don't have that for the Apollo images, right? We didn't know. Like we have a kind of an estimated trajectory, but we don't have truth data for the Apollo images. It ends up being easier to render images of the moon, to say, I'm going to create a 3D model of the surface of the moon, and I'm going to render the moon for a given location, for a given initial latitude, longitude, altitude, and viewing direction. But then now you're part of your whole pipeline for crater navigation is now image rendering. You've kind of added a fifth step, which is no small feat either. That's its own whole bag of worms. The neural net will draw bounding boxes around craters. And or attempt to fit limb points. Or sorry, not limb points, rim points. Nope. Sorry. Limb points is OBNAV. These are rim points. So imagine that you've got crater here, here, crater here. You'll have neural nets that just draw bounding boxes and go, yep, found crater, it's right here. But that really won't do. We actually need rim points. Or you'll get one that says, yeah, I got you, boss. There's your crater. And it's like, I think I could have traced it better if I gave a crayon to a toddler. So neural nets are kind of still in their infancy in this area. Now, I maybe I'm being a little bit too pessimistic. There are some pretty darn good neural nets that can do a decent job of this, but in much the same way that really nailing your horizon point for OpNav is critical to the rest of the math problem, really nailing your rim points with your neural net is critical to the rest of the crater navigation problem. And in general, this is the performance bottleneck. This is what I've seen to be kind of, if something is going wrong, it's, the neural net kind of botched some of our rim points. And like, well, there's nothing you can do with that. You have bad rim points. So to be clear, on homework 7, you will just approximate the centroid of your favorite, we'll say your favorite 4+ craters by eye. In much the same way that on homework 6, you can just click your favorite horizon points of Pluto to solve OpNav. You can just pick the centers of craters. Not going to make you code up your own crater detection algorithm. That would be way outside of scope for this class. So that's enough for homework 7. Okay, next is crater databases. You might say, Paul, surely we don't have just a list of where all the craters are on the moon? And I would say we do, and don't call me Shirley. Not necessarily every single crater, but certainly enough craters to be useful for navigation. So I'll just mention scientists have already created databases of lunar and Martian craters. These are similar to star catalogs. These often contain among other things, we've got center, latitude and longitude, diameter, and ellipticity, which is similar to eccentricity, right? Because craters are generally circular, but not always. They can have a little bit of eccentricity. I'll say there are, for all practical purposes, an infinite number of craters on the moon. Just like there are, all for practical purposes, an infinite number of trees on the Earth, right? Or when you look at the sky, an infinite number of stars, right? For practical purposes. We don't need all of them. That's the thing. You only need some of them. So I'll say, but we can create mostly complete global databases of large craters. The same way, I'm going to try to spell craters a little bit better. The same way that we have mostly complete databases of the bright stars, we can have mostly complete databases of the large craters. So one example is what's called the Robbins Crater Database. Has more than 2 million entries. And includes almost all craters with a diameter of greater than 1 to 2 kilometers. And I'll say this is plenty for navigation. Okay. Once again, I'll say on homework 7, not necessary. You do not need to pull down the Robbins Crater Database. On homework 7, you can identify craters manually. Using the Arizona State University LROC quick maps data, which I link in the handout to the homework assignment. Basically, there's a website which is pretty darn similar to just Google Moon or Google Earth, where if you hover over individual craters, you can find, if you click a mouse point, you can find latitude, longitude, altitude of that point on the surface of the moon. Quick maps, not to be mistaken for quick maps, which is a different concept. But anyway, that is our crater database discussion. Questions on crater detection or crater databases? Otherwise, we'll keep on cruising. And we're almost done. Okay, next is invariant-based crater ID. So we can use techniques from invariant theory to determine the number of invariants for a set of D craters. This is much easier said than done. Okay. Recall from our star tracker unit that if we have D stars, those will have 2D minus 3 invariants if camera attitude is unknown. Okay. If we consider D convex, which is basically just a two-dimensional ellipse, we have D convex in 3D space with no other constraints. There are no invariants. You get lazy. That's the does not exist symbol. There are no invariants. If we just have 3 crater rims floating in space in any random orientation for each and relative configuration, there's nothing about those 3 that is invariant to observer geometry, if that makes sense. So if instead we consider D conics, which are on the surface of an ellipsoid, like the surface of the moon or the surface of a sphere, then there exists 3D minus 6 invariance. And if we consider D conics on the same plane, let's say we're really low over the moon, the region that we're photographing can be approximated as a plane. Consider D conics on the same plane. Then we end up with 5D minus 8 invariance. Okay. Thus, we can leverage invariance for crater ID using high and low altitude images, right? Images that contain a lot of the lunar surface and kind of low images where it's basically a plane underneath you. We can leverage invariance for crater ID using high and low altitude images. So the way we would do this, a navigator must use a crater database to construct an index of invariance for either pairs or triads of craters. And this must be done before flight. And this index must be rapidly searchable. We have to constrain our index size, right? Just like with our star ID. Don't want our index to be huge. It can be too difficult to carry around with us. And we will focus on the craters the spacecraft is most likely to see. So what do I mean by that? We ignore star pairs where the interstar angle is larger than the field of view of the camera, because you will never see that pair of stars in a single image. Similarly, we can ignore craters that are too far apart for a given mission profile. Let's say you know you're going to be doing a low altitude flight over the moon. And let's say you know you're going to be doing a low altitude flight over the moon's equator, right? Then you don't need craters that are near the poles of the moon, and you don't need craters that are too big to fit in the field of view of the camera. So it is helpful to stop and think about only including the bare essential craters when you start your mission. And I will say on homework 7, scrolling for a second, yeah, on homework 7, none of this is necessary. You are identifying craters by eye. But this is just FYI. Okay, and then finally the fourth step, and we are going to drill down on this. Yes, Michael.
Is there like a horizon constraint on craters where it's like, if they're like for lack of a better term, on opposite hemispheres, can you constrain like how far they are apart within an invariant?
I'm not sure I'm tracking the question. So when you mean constrain them, do you mean like we're not considering them for this crater database, or what do you mean?
Like when you create invariants, is there like a limiting factor on like, well, these craters are obviously like one's on the front side, one's on the back side of the moon, like they can't possibly form a triad?
Well, they could form a triad, right? The same way that any two stars can form a star pair, right? So there's nothing inherently about the invariant itself where you can go, oh, there's no way those would be in the same image. You would need to kind of pre-compute and go, oh, here's one crater at this lat long, here's another crater at this lat long. The distance between them on the surface of the moon is too great. We would never see those in a single image. Forget those two, that sort of thing. But that doesn't show up directly in the invariants themselves in a way that is clear to the human brain what's happening, if that makes sense.
Okay, yeah, that makes sense.
Okay, last bit, and I'm just going to set up this problem and then we will call it for the day because I want to talk about homework 5. But we will start on this fourth one, which we will spend some time on, and that is the relative pose estimation. That's the meat of homework 7, is I want you to code up your own pose solving algorithm here. So spacecraft pose estimation. Okay. The final step is computing the relative position and attitude of the spacecraft and the planet, or the moon in this case. And remember that position and attitude, that's pose. So we don't know velocity, but we know position and attitude of moon and our spacecraft. Okay. There is a way, I'll say it is possible to leverage apparent crater shape and size when doing this. But we'll leave that out of this discussion. The idea there was like, oh, this crater appears highly elliptical. I have to be looking at it kind of slantways. And that means that my altitude needs to be between this and this. There's ways to kind of bake in the apparent shape of your craters into your solution. What we're going to do in this class is just focus on crater centers and their corresponding latitude and longitude. So if relative attitude is known, so e.g. you also have a star tracker, then this is triangulation. We already talked about this. Right. This is basically homework 3, right? We had something where I gave you the line of sight direction to known craters, I gave you their latitude, longitude, and you had to solve for this using triangulation. However, if attitude is unknown, so in general, we want position and attitude. So this is what's known as the perspective endpoint problem, or PNP problem. So homework 7 is solving the PNP problem. And the PNP problem is, given n image coordinates, and corresponding world coordinates, estimate camera pose. So you see how this is kind of the cooler older brother to Waba's problem, where with Waba's problem, there's no discussion of position, it's just rotation. Here, there is a position and a rotation, which we're solving for at the same time. So PNP, especially in the robotics world, this is a very well-studied problem with many published solutions. Yes, Nick.
You said before that there was no image processing on homework 7. How are we able to do that if we need the image coordinates of the center of the crater?
Oh, you just click on them. You just say, all right,
Oh,
I think
okay.
it's that point. Yeah,
Okay.
just like with homework 6, right? There's not really any image processing for homework 6. You're just trying to find, okay, I'm going to click on this horizon point and just write down its number and hard code it into my script. That's fine. I'm not asking you to find, like to write a script to find crater centers. You can just load them up in Paint and then just find the pixel coordinates, however you want to do it. But yeah, like I was saying, for a PNP problem, this is a very well-studied problem. There are MATLAB and Python built-in functions to do this, which you're welcome to use to check your answer, but I'd like you to do your own answer as well. So there are MATLAB and Python built-in functions. What follows in the next lecture is a method that will work for four or more coplanar points. And I'll just add the caveat that this is by no means the best way to solve the problem. But it makes sense to me. So there are better ways out there to get your answer, but this is good enough. It hopefully makes intuitive sense. At least it makes intuitive sense to me. I'd like to make it make intuitive sense to you. We will go through how to solve for your position and your orientation given corresponding points. And that's going to be about 2.5 pages worth of notes, which is less than half a lecture. So we're going to hopefully finish that up really early next time. And then we'll just stop and we'll talk about homework 5. But anyway, any questions on the lecture material for today? Otherwise, we can stop recording and move to like a little mini office hours. Okay, cool stuff. Thanks, everyone. I'm going to stop the recording, but by all means, stick around.